Section 2.2 to Section 2.3 Understanding Standard Deviation. The formula for calculating the sample standard deviation, S, is slightly different from the population standard deviation formula. When working with sample data, we use a modified formula to account for the fact that we are estimating the population parameters based on a subset of the data. Here are the steps to calculate the sample standard deviation. Calculate the mean, average, of the sample data. For each data point, subtract the mean and square the result. Calculate the sum of the squared differences obtained in step 2. Divide the sum of squared differences by n1, where n is the total number of data points in the sample. Take the square root of the result from step 4 to obtain the sample standard deviation. Mathematically, the formula for calculating the sample standard deviation, S, is as follows: S equals square root, sigma, 11, x, caret 2 slash, n1, where S represents the sample standard deviation, 11 represents each data point in the sample, x represents the mean of the sample data, n represents the total number of data points in the sample. The main difference between the population and sample standard deviation formulas is the denominator. In the sample standard deviation formula, we divide by n1 instead of n. This correction factor, called Bessel's correction, adjusts for the fact that using a sample instead of the entire population introduces some degree of uncertainty in our estimation. By using the sample standard deviation formula, we get an unbiased estimate of the population standard deviation based on the sample data. It is important to note that the sample standard deviation tends to slightly underestimate the population standard deviation, especially for small sample sizes. 2.3 Interpretation of standard deviation. Standard deviation is commonly used as a measure of dispersion and volatility in statistics and finance. It quantifies the amount of variability or spread within a dataset or a set of observations. The interpretation of standard deviation depends on the context in which it is applied. Dispersion. Standard deviation measures the average amount by which individual data points deviate from the mean. A higher standard deviation indicates a greater dispersion or spread of the data points, implying that the values in the dataset are more spread out from the mean. Conversely, a lower standard deviation suggests a narrower range of values, indicating less dispersion or a more concentrated dataset. For example, consider two datasets, dataset A, 5, 10, 15, 20, 25, dataset B, 10, 10, 10, 10, 10. In dataset A, the values are more spread out, resulting in a larger standard deviation. In dataset B, all values are the same, resulting in a standard deviation of 0. Volatility. In finance and investment analysis, standard deviation is often used to measure the volatility of an asset or a portfolio's returns. It provides a measure of the historical or expected price fluctuations or returns of an investment. Higher standard deviation in this context indicates greater price or return volatility, suggesting a higher level of risk associated with the investment. Lower standard deviation, on the other hand, implies lower volatility and potentially lower risk. For example, consider two stocks, stock A, standard deviation of returns equals 10%, stock B, standard deviation of returns equals 5%. Stock A has a higher standard deviation, indicating greater volatility and higher risk compared to stock B, which has a lower standard deviation and is considered less volatile. In summary, standard deviation serves as a measure of dispersion and volatility. It quantifies the spread of data points around the mean, providing insights into the variability of the dataset or the historical volatility of an asset or investment. Understanding the standard deviation helps assess the level of risk, make informed decisions, and compare different datasets or investments. When comparing standard deviations across different datasets or populations, it's important to consider the context and the characteristics of the datasets. Here are a few key points to keep in mind when comparing standard deviations. Magnitude of standard deviation. Compare the magnitudes of the standard deviations directly. A larger standard deviation indicates greater variability or spread in the data, while a smaller standard deviation suggests less variability or a more tightly clustered dataset. However, be cautious when comparing standard deviations across datasets with different units or scales, as the magnitude alone may not provide a meaningful comparison. Relative standard deviation. Consider the relative standard deviation, which is the standard deviation divided by the mean or another appropriate measure of central tendency. This ratio helps to compare the spread of data relative to the average value. A lower relative standard deviation indicates a smaller variation relative to the mean, while a higher relative standard deviation suggests a larger variation relative to the mean. This comparison can be useful when dealing with datasets with different means or scales. Sample size: take into account the sample size or the number of observations in each dataset. Smaller sample sizes tend to result in less precise estimates of the population standard deviation, leading to higher variability in the calculated standard deviation. Therefore, comparing standard deviations from datasets with significantly different sample sizes should be done with caution. Distribution shape: consider the shape of the data distribution in addition to the standard deviation. Two datasets may have similar standard deviations, but one may have a more symmetrical distribution, while the other may have a skewed or non-normal distribution. In such cases, additional measures or visualizations, example, histograms, box plots, can provide a more comprehensive understanding of the data distribution and help in making meaningful comparisons. Contextual factors: consider the context and the nature of the datasets you are comparing. Different datasets or populations may have inherent characteristics that affect the variability or spread of the data. For example, comparing the standard deviations of test scores across different grade levels or comparing the volatility of stock returns in different industries may require additional contextual analysis and understanding of the underlying factors influencing the variability. In summary, when comparing standard deviations across different datasets or populations, it's crucial to consider the magnitude, relative standard deviation, sample size, distribution shape, and contextual factors to make meaningful and accurate comparisons. It's important to interpret the standard deviations in the specific context and take into account any inherent characteristics of the datasets being compared.